So why are we interested in wave energy in Ireland? Well, this is the global distribution of wave energy density, and unfortunately Taiwan is covered up on the right side there. The brighter the colours in this map, really, the higher the energy density. So you can see that if you look at the colours there on the west coast of the US, you've got maybe a light blue. On the west coast of Ireland, you've got a lime green. On the west coast of Chile, you've got a lime green. West coast of Australia, you've got a lime green. So really, those are the four locations where the wave energy density is very high. The top right-hand map then is a zoom in, if you like, to the energy densities. And typically off the Irish coastline, the energy density is 70 kilowatts per metre. So that is a huge amount of energy, 70 megawatts per kilometre. And so then we have this great interest in the conversion. So as I say, if you take the accessible resource in Ireland, that is really the technically feasible resource that you could convert into real electricity, then this study by ESP International showed that we could generate 20 terawatt hours per year if we develop all of the energy resource which is feasible. The electricity usage in 2010 was 34 terawatt hours per year. So you can see there is a huge potential for wave energy to contribute to the Irish electricity demand. So that's really why we're very interested in wave energy in Ireland, is because it has this huge potential to contribute to the energy demand. So in terms of moving things forward, the government has a plan. We have a strategy for implementing the plan, and the government itself has made a commitment to funding this plan and strategy moving forward. So we have the white paper on energy development, which makes this commitment to 500 megawatts by 2020. And then we have this ocean energy strategy, which shows the sequence of developments of the industry from virtually nothing into a fully commercial industry by around 2015 or 2016. We also have a roadmap out to 2050, which says that perhaps we could even produce 1,500 megawatts by 2030 and 6,000 megawatts by 2050. And if we have interconnections to Europe, then we could be exporting this electricity to Europe by 2050. So the government has a long-term vision as well. Now, in terms of the development of ocean energy systems, and this applies both to wave energy and to tidal energy, we've been involved in the development over many, many years. We don't have a specific device in my own research centre. What we provide is technical support for other people who are developing devices. So we've been supporting wave energy developers to develop their schemes from concept to commerciality. And we found over the years that many of the people who come along to us are inventors. They have a fantastic idea, they've been at the restaurant, and they've maybe drawn a little sketch on the napkin for their idea, and they've managed to persuade somebody to give them a little bit of money, and next thing they want to do is build a megawatt-sized device in the ocean. And obviously that is a recipe for disaster. So we've been pushing over the years that what you need to do is a sequenced development, increasing the scale every time, and reducing the risk, increasing the understanding. And this is really standard engineering development practice. I mean, the thing you do, Boeing do it for developing airplanes, everybody who's involved in large-scale engineering developments can see this development process being required. Most of the people involved in ocean energy, really, many of them are not engineers, many of them are not even technical. So we've been trying to insist on this protocol for development to show people that it is needed in terms of increasing the confidence that these things will work when they go to sea, because they are exposed to extremely violent, extremely harsh environment. So the idea is that you start off with small-scale models of the wave tank, supported by numerical method modeling, larger scale models of the bigger wave tank, again supported by numerical modeling, moving into phase 3 then, which is maybe going off into the open ocean, but at scaled sites where the conditions are not extreme. And And once the machine survives that and produces electricity, then you can think about moving into the open sea and with a large-scale device, and then moving on into the commercialization. So we see that as an essential development path for anybody following the ideas from concept to fruition. And as I say, that probably applies in the tidal energy concepts as well as in the wave energy concept. So the US Department of Energy have recently become involved in ocean energy. They call it marine hydrokinetic energy, and they have adopted a similar type of concept, adapted from the space industry in the US. They have 9 levels of what they call TRL, which is technology readiness level, and they correspond in groupings to the 5 phases that we have in our protocol. And the US government will not fund proposals at any of these TRL levels unless the developers or the proposers can show that they already have experience at the lower levels. So if you cannot demonstrate that your device or your idea has been tested at the TRL level 5, you will not get funding for a TRL level 6 type of demonstration. So it's used by the funders, it's used by people investing in companies for really assessing where things are. So this is happening, and obviously to allow this to happen, you need testing facilities to allow this to go on. If you look at the Irish west coast, this is our typical wave climate. This is maybe over a couple of years. Each of the dots corresponds to one of the wave conditions. And you can see that the wave conditions in the Irish context, they go up to a significant wave height of around 14 meters. At least maybe 2 or 3 hours in the year you get 14-meter wave heights with wave periods of 12 to 13 seconds for TZ. And the range is from 0 to 14 and from about 4 seconds to 14 seconds in the overall spread of things. So these are the conditions that the wave energy machines must deal with in their lifetime. The average output, as I said, or the average input is 70 kilowatts per meter, but up at these times up here, you're getting maybe 2,000 kilowatts per meter with the waves of that big. So the machine has this engineering challenge to be able to resist the extreme of these wave forces. And that really is the issue in terms of engineering these devices at a reasonable cost. So in order to do that, as I say, you need to develop the equipment and the capabilities to be able to test at these different scales. This is just to illustrate to you the sort of wave conditions that we get in Ireland. This is not an extreme wave. These are cliffs on the west coast of Ireland, and these are 100 meters high. There to there is 100 meters. So that gives you an idea. You've got probably green water up here to about 20 meters, and then you've got spray going up to about 100 meters there with the waves breaking at the cliff. So these are typical of the conditions that we have on the west coast of Ireland. As I say, we need facilities then to be able to test these devices at all of the phases of development. So in my own research center, we have a wave basin 25 meters long and 18 meters wide with 40 wave paddles. And in that we can test devices of maybe 1 to 40 and 1 to 60 type of scale in the phase 1 and phase 2. We're building a new wave basin, which I'll talk about in a minute, which will allow us to do the phase 3 type of testing. We also then have what I call the intermediate scale test site in the ocean. This is a quarter scale test site, and it exists on the west coast of Ireland in a place called Galway Bay. So this is Ireland, the island of Ireland. Cork is on the south side here. This is Galway Bay. And Galway Bay is a semi-enclosed bay with a series of islands at the mouth. And within this bay, we get wind-generated waves primarily. And those wind-generated waves are really very good at a quarter scale of the open ocean. Because the real problem with waves is that you have to scale 2 parameters. You will scale the wave height and the wave period. If you're doing a tidal stream project, you probably can look for a lower speed, and that is the scale. It's a 1 parameter problem. The same with wind turbine developments. You can develop a wind turbine in a lower wind speed and then scale it up to the open ocean or the open location with higher wind speeds. With waves, you cannot do that. You cannot just put your machine in a place where the waves are smaller, because you usually find that the wave periods don't change very much. So you need to be in this area which is semi-enclosed, where both the wave heights are reduced, but the wave periods are reduced as well because of the limited fetch for the wave generation in this bay. So this is the location of our quarter-scale test site in Ireland. It has a water depth of roughly around 20 meters at this point, and the waves, as I say, scale to the open ocean. And we have a problem, though. It would be rather nice if the islands at the mouth really block the whole of the bay. But we do get this problem that because of the gaps between the islands and the mainland, we get offshore swell coming in, which contaminates some of the waves. So you have to be a little bit careful that you only analyze data related to the local wind seas, which are the scale. So if you go back to